This is Math 2115, Alternative Delivery for 26 March 2020. Please have pencil and paper in hand and engage actively in the learning. I want to open by again commending you for being flexible and working hard in this environment. I really do think that with our combined efforts, like these trees will withstand the winds that are out there and thrive going forward. Teaching and learning can continue unabated, and I'm in the process of grading things. There will be other opportunities for you to grade. Grades will be rendered, and educational plans need not be deferred. And so I appreciate your patience and fortitude in sticking with things. I expect that for many of you there can be a happy ending. Last time we proved these two theorems. One's a theorem, one's a corollary. So if a graph has what we call an Euler circuit, that means it visits every edge once, then every vertex of the graph has positive even degree. But the contrapositive was also useful, and that was if some vertex has odd degree, then the graph does not have an Euler circuit. We also concluded by stating this theorem, which we paused before proving because it's kind of an involved proof. But today we're going to say that even though the converse is not exactly true, if we mix in the notion of connectedness, then there is a converse of sorts. If a graph G is connected and the degree of every vertex of G is a positive even integer, then G has an Euler circuit. And in contrast to many proofs that we will do, this proof is constructive in nature. So this ends up not only telling you it exists, but how to find it. So here we go with the proof. This is if and then. So suppose we start with any connected graph, and suppose that every vertex is a positive even integer. That's the if part. So we have to find an Euler circuit for G. So we're going to begin by constructing a circuit C by the following algorithm. We pick any vertex V of G at which to start. And this step can be accomplished because the vertex set of G is non-empty by assumption. If it were empty, the theorem would be true anyway. It's a if part with a false hypothesis. Number two. Then we pick any sequence of adjacent vertices and edges, starting and ending at V, and never repeating an edge. And we're going to call this resulting circuit called C. Now we do have a circuit, and let's talk about why we can do that. Step 2 can be performed for the following reason. Since the degree of each vertex of G is a positive even integer, as each vertex of G is entered by traveling on one edge, either the vertex is V itself, and there is no other unused edge adjacent to V, or the vertex can be exited by traveling on another previously unused edge. Since the number of edges of the graph is finite, by definition of a graph, the sequence of distinct edges cannot go on forever. The sequence eventually returns to V because the degree of V is a positive even integer. So each time an edge leads out of V to another vertex, there must be a different edge that connects back. So what we've done is we've created a cycle, but it's not a cycle for the entire graph. But we must check. So we check whether C does contain every edge and every vertex. If so, we're finished. And if not, we have additional steps, and we're really going to be doing kind of the same things over and over again. First step, 3A, is we remove all edges from the existing cycle from G, and also any vertices that become isolated when the edges of C are removed. And we call this subgraph G prime. We should note that G prime may not be connected, but every vertex of G prime has a positive even degree, Since we've removed the edges of C, that removed an even number, and so there has to be an even number left, and so that's why we can do step 3A. Step 3B then, we pick a vertex W that is common to both C and the subgroup G prime, subgraph G prime. There must be at least one such vertex since G is connected. So we're going to pick then, so we pick W to be that one. Then we pick a sequence of adjacent vertices and edges of G prime, starting and ending at W, never repeating an edge, and call this C prime. Now this can be done for the same reason that we talked about for step 2 above. So step 3D, we patch C and C prime together to create a new circuit called C double prime as follows. Start at V, follow C all the way to W, and then follow C prime all the way back to W, and after that continue along the untraveled portion of C and return to V. Then we let C equal C double prime and go back to step 3 and continue with the process. Since the graph is finite, execution of these steps outlined in this algorithm must eventually terminate. At that point, an Euler circuit for G will have been constructed via this technique. Now it is possible, depending on where you start, to get different Euler circuits to be produced, but you can verify that this will in fact produce a circuit. So here's a problem doing that. So I hope you made note of the steps, and I'm going to ask you to use the theorem first of all to check that there is an Euler circuit here, and then use the algorithm to find an Euler circuit. So hit pause and invest some time in doing the problem, please. And then let's return and see how you did. Let's see how you did. It's sufficient for us to identify the degrees of all the vertices, and here we show that the degrees of all the vertices are in fact even numbers. So that means that there is going to be, and the graph is connected, that means it is going to have an Euler circuit. When we use the algorithm of that theorem, we let V equal A and begin with C this way. Now, so we begin with A and we go this way, this way, this way, and then we go back. So we've created a circuit right there, but we didn't cover all the vertices. So now we're going to take a vertex that is common to C and the remaining world, and that's going to be D in this case. So C is not an Euler circuit, and we have D, so we're going to let C prime be, and we'll complete a cycle with D. So the cycle with D will start here. It will go here 5, 6, 7, 8, and 9. So we go all the way back, and now what we have is we can patch C prime into C, and we go this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So now we have the C prime. And now we set C equal C double prime, and C is represented by the edges labeled below. And now what we do is we get this part of it with the thing that is in common is E, so we will complete this. And so what we have then is an Euler circuit. Every edge is traveled once and every vertex is visited. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that is the construction that you can do to construct one once you've verified that in fact it exists. It is easy to show that any graph with an Euler circuit is connected, and so if you take that kind of a trivial result with the results of the theorem that we just did, we do have an if and only if. A graph G has an Euler circuit if and only if G is connected and every vertex has positive even degree. There's a corollary to this that gives a criterion for determining when it is possible to find what we call a walk from what we did call a walk already, I guess, from one vertex of a graph to another, passing through every vertex of the graph at least once and every edge of the graph exactly once. And we have a definition for that before we state the corollary. And so the definition, we're going to call this an Euler trail. So let G be a graph and let V and W be two distinct vertices of G. An Euler trail from V to W is a sequence of adjacent edges and vertices that starts at V, ends at W, and passes through every vertex of G at least once, and traverses every edge of G exactly once. So the corollary then is, if you have a graph and let V and W be two distinct vertices of G, then there's an Euler trail from V to W if and only if G is connected. V and W have odd degree because you start and stop there, and all other vertices have positive even degree. Here's a problem where I'm asking you to find an Euler trail. This is a problem that people do study when they're establishing walking paths for museums and things like that. So we're going to find an Euler trail here. The floor plan shown below is for a house that is open for public viewing. Is it possible to find a trail that starts in room A, ends in room B, and passes through every interior doorway of the house exactly once? If the answer to that is yes, and you explain, then find such a trail. So hit pause, do the problem, and then return, and we'll see how you did. Let's see how you did. Well, the degree of A and B are both 1, and every other node has a degree that is an even number, and so there certainly is an Euler trail, and so we know there is one, and one such one goes this way. We go from A to G to H to F to E to I, back to H again, back to E again, to K, J, D, C, and B. So that works, and that's what you should have found. And I will tell you that when I was a student, I remembered that Euler was associated with the edges. There's another kind of circuit that we'll study that's associated with the vertices, and these are called Hamiltonian circuits, and those are named after the great Irish mathematician William Hamilton. There are other things that are named after Hamilton in addition to these Hamiltonian circuits. In fact, there is a partial differential operator that's called the Hamiltonian. But anyway, here's the question that's has been answered, and then the one we're looking ahead to answering. The one we have answered is, given a graph G, is it possible to find a circuit for G in which all the edges appear exactly once? We've answered that. That was the Euler circuit problem. A related question is this: given a graph G, is it possible to find a circuit in which all the vertices of G, except the first and the last, appear exactly once? Now this turns out to be a very different kind of problem, and in a sense much more difficult. In operations research terminology, this is called the traveling salesman problem, and after our spring break we will begin addressing that. But first, let's talk about a few different graphs. One thing that people have talked about sometimes is the idea of there being 6 degrees of separation, meaning that you can connect any two people with, oh, he knows them, by only 6 steps. Now, this was originated a long time ago and is kind of a sociology hypothesis that people have set forward. But I tell you that there's a great deal of truth in this, because I'm going to just give you 2 examples from my own life. I can connect myself to Albert Einstein with less than 6 degrees of separation. I used to work with a mathematician who was even older than me, named Peter Rothmeller, And Peter Rothmiller took, so me to Peter is 1 degree of separation. Peter took a class at the University of Michigan with Paul Halmos when he was a graduate student. And so that is a second link. Turned out Paul Halmos was an apprentice to John von Neumann at Princeton's Institute of Advanced Studies. And John von Neumann was a colleague and a respected colleague of Albert Einstein at Princeton's Advanced Institute of Technology. So you see, I took me and Albert Einstein, and that was like 4 or 5. It wasn't 6 for sure. Another thing is I certainly can connect myself to Pope Francis with less than 6 steps, because I know a pope and the pope knows bishops, or I know a priest, I guess. I know a priest and the priest knows bishops, the bishops know archbishops, the archbishops know cardinals, and the cardinals certainly know Pope Francis. This has been generalized, and they've talked about an idea called the 6 degrees of Kevin Bacon, and that really became kind of an interesting thing, because Kevin Bacon, as a young actor, appeared in many films that had very venerated and older actors who'd been worked with many people over time. And so that's another game that you may have heard of related to this. In math, there's also something that is like this. The great mathematician Paul Erdős was one of the most prolific mathematicians of all times. He was an author or co-author of nearly 1,500 papers. Mathematicians who co-authored a paper with Erdős were said to have Erdős number 1. Mathematicians who did not co-author a paper with Erdős, but who co-authored a paper with a mathematician whose Erdős number was 1 are called Erdős number 2, and so on and so forth. And in fact, the author of the textbook we're using co-authored a paper with this fellow who co-authored a paper with someone else, and so on and so forth. And he has an Erdős number of 5. And you can develop a graph theory model where you have adjacency. I'm not going to make you do this, I suppose, but in your model, what is an Erdős number? And this is the number of hops required to get back to Erdős, the number of links in your graph, the number of edges to get back to Erdős. Okay, this is maybe a more interesting example for you. Sometimes we have a precedence graph, and the vertices model certain actions. A vertex might model a statement in a computer program. There is an edge from vertex V to vertex W if the action modeled by V must occur before the action modeled by W. And I'm asking you to do 51 and 52. Draw a precedence graph for the computer program shown in 51 and 52. I'm going to ask you to pause now, and I'll return and we'll talk about the solution. So pause now, and we'll return soon. Let's see how you did. And I guess here are answers. Before you can do this step or this step, you have to know about x being 1. So this step has to precede those 2. You have to know y is 2 before you can do either of those steps, and you have to know z is 3 before you can do either of those steps. So that tells you what you have to complete before you can complete those steps. And here you have to have a, b, and c. So and actually here you don't know c yet because you need to do c plus 1. So you have to know what c is here, then what is the new c, because this assigns c plus 1 to the old value of c, and then you can add a, b, and c. So that should be the precedent graph that you have for that one. For 52, likewise, you can see that we go from that actually 52 is more straightforward, I think. Those are examples of things called precedent graphs. And we're going to